Hello everyone, welcome back to Maths with Anu. In the previous video, we learned the basic idea of continuity and solved the first set of NCERT questions. In today's lesson, we are going to learn two very important theorems that appear throughout this chapter. Once you understand these theorems, many NCERT questions can be solved in just a few seconds without lengthy limit calculations. So don't just memorize the answers, try to understand the logic behind every step, because that's what will help you in board exams as well as competitive exams. Before we start solving questions, let me ask you something. Suppose I give you the function x squared plus sin x. Should we calculate left-hand limit, right-hand limit, and function value every single time to check continuity? Imagine doing that for hundreds of questions. It would take forever. Mathematicians noticed that certain types of functions are always continuous. So instead of proving them again and again, they developed useful theorems. These theorems allow us to conclude continuity almost instantly. Let's understand the first theorem. Suppose I have two functions, f of x and g of x. Both of them are continuous. What does continuous really mean? It means you can draw their graphs without lifting your pen. There are no breaks, no jumps, and no holes. Now think about adding these two functions together. If one graph has no break and the other graph also has no break, can adding them suddenly create a break? No. Nothing discontinuous is being introduced. Exactly the same logic applies to subtraction and multiplication. That is why the sum, difference, and product of two continuous functions are also continuous. Now, you might wonder, if addition, subtraction, and multiplication always work, why is division treated differently? Let's think about a simple example. 1 divided by x. What happens when x becomes 0? We cannot divide by 0 because the value becomes undefined. So even if the numerator is perfectly continuous, the denominator can create a problem. That's why this theorem has one important condition. The denominator must never become 0 at the point where you are checking the continuity. Let's apply this theorem. Take the function x squared plus sin x. We already know x squared is continuous everywhere. We also know sin x is continuous everywhere. Since both functions are continuous individually, their sum must also be continuous. Notice that we didn't calculate even a single limit. This is exactly why the theorem is so powerful. Now let's move to another important theorem called the composition of continuous functions. The word composition simply means one function is placed inside another. The theorem says that if both functions are continuous wherever they are used, then the combined function is also continuous. Let's understand this theorem with the help of an example. Here, the inner function is x squared plus 1 and this is the continuous function everywhere. And the outer function is square root of x. So this is also continuous for positive numbers. Therefore, their composite function, which is under root x squared plus 1, will also be the continuous function. Now let's solve the exercise 5.1 questions with the help of these theorems. So we will solve first question number 15 from exercise 5.1. Notice something carefully. Each individual piece is either a polynomial or a constant function. Both of these are already continuous. So where can discontinuity occur? Only where the rule changes. That means we don't need to check every value of x. We only need to check the boundary points, which are x equals 0 and x equals 1. Let's begin with x equals 0. Approaching from the left, we use first expression. Approaching from the right, we use the second expression. Both limits become 0. The function value is also 0. Since all three are equal, there is no jump and no hole. So the graph passes smoothly through x equals 0. So this function is continuous at x equals 0. Now let's examine x equals 1. From the left side, the function approaches 0. From the right side, it approaches 4. Notice something important. The graph suddenly jumps from 0 to 4. Whenever the left-hand limit and right-hand limit are different, the graph cannot be connected continuously. So this point is discontinuous. So we can say that the function is discontinuous at x equals to 1. So our final conclusion is simple. The function is continuous at x equals 0, but it is discontinuous at x equals 1. Now let's solve question number 17 from the same exercise 5.1. This question introduces an unknown. Instead of checking continuity, we must find values of a and b that make the function continuous. The definition of continuity doesn't change. At the joining point, the value from the left and the value from the right must be exactly the same. Substitute x equals 3 into both expressions. The first expression gives the value from the left. The second expression gives the value from the right. Since function is continuous, these two values must be equal. Now, it's just a simple algebraic equation. After rearranging the terms, we obtain a minus b equals 2 by 3. So this is the relation between a and b. Whenever you see unknown constants in continuity questions, remember this approach. Use continuity condition first, then solve the resulting equation. Let's move to the next question, question number 20 from the exercise 5.1. This question looks like a limit problem, but it's actually testing whether you remember Theorem 1. Instead of calculating limits, ask yourself one question. What type of functions do I have? A polynomial function, a trigonometric function, and a constant. All three are continuous individually. According to Theorem 1, their sum and difference must also be continuous. Therefore, applying the Theorem 1 here, we can see that difference of continuous functions and the sum of continuous functions will also be continuous. That's all. Sometimes understanding the theorem saves more time than calculation. Therefore, f of x is continuous at x equals to pi. Here is the another question from exercise 5.1, question 21c. Now, again, don't rush into calculations. First, identify the functions. Sin x is continuous. Cosine x is also continuous. The theorem tells us that the product of two continuous functions remains continuous. Whenever you recognize this pattern in exam, you can use the Theorem 1. Therefore, the product of sin x and cos x is also continuous for every real number. Now, let's check question number 24 from the exercise 5.1. This is one of the most famous questions in the continuity chapter. Many students get scared because they see sine of 1 upon x. But don't worry, we will understand the idea instead of memorizing the solution. For all real values of x except for 0, we know that x squared is continuous and sine of 1 upon x is also continuous. Therefore, x squared multiplied with sine of 1 upon x is also continuous. Notice that the difficult part is sine of 1 upon x. Can we predict its exact value near 0? No, because it keeps oscillating very rapidly. But there is one thing we always know. No matter what x is, sine can never become greater than 1 or smaller than minus 1. This simple observation becomes the key to the entire question. Now, multiply every part of the inequality by x squared. Why are we doing this? Because x squared is the factor present in our function. We are transforming the inequality so that the middle expression becomes exactly the function whose limit we want. Now observe the left boundary and the right boundary. As x approaches 0, both become 0. Imagine squeezing the middle expression between two walls that are moving closer and closer together. Since both walls finally meet at 0, the middle expression has no choice but to reach 0 as well. This is the entire idea behind the squeeze theorem. The limit at x equals to 0 is 0. The function value at 0 is also 0. Since these two values are equal, the function is continuous at 0. And because it is already continuous everywhere else, we conclude that the function is continuous for all real numbers. Great job! In this video, we learned two important continuity theorems and used them to solve several NCERT questions. In the next part, we will solve remaining important questions of exercise 5.1. If this lesson helped you, don't forget to like the video, subscribe to Maths with Anu and keep practicing. See you in the next class.